Now we take a look at the specification of the spatial lag, Probit, and Tobit models. And first we look at the Probit. And the way we approach this is by spelling out the reduced form. And if you remember, the spatial lag model has a spatially lag dependent variable on the right-hand side, which is really endogenous and causes simultaneous equation bias. So we need to move that out of the right-hand side, and the result is the so-called reduced form, which is the expression on the slide with y star equal I identity matrix minus rho W inverse. W is a weights matrix, x beta, that's the inverse of the spatial filter, and then the same reduced form for the error term, I minus rho W inverse times the error term U. Now, a couple of things are going on here. First of all, as we've already mentioned a number of times, the dependent variable is not observed, and so this expression pertains to the latent dependent variable y star. Secondly, this is a multivariate expression. So this is in a matrix and vector notation. It's not expressed as the typical u sub I and then xi sub I. We have to look at the whole vector, random vector together because of its multivariate nature. And a third characteristic is that the spatial autoregressive parameter, the rho, is a part of both the regression model, the I minus rho W inverse x beta, but also part of the distribution for the error term. So the error term becomes multivariate normal if we assume a variance of 1, which we do for identification purposes. Then the variance covariance matrix of the error term is I minus rho W prime I minus rho W, the whole thing inverted. So this is a complex variance covariance matrix. Obviously it has spatial autocorrelation, but we also have seen that it is heteroscedastic. So this creates a lot of problems because our traditional threshold condition is expressed for each observation. For each observation, we determine the probability of observing a 1 or a 0. And to express this formally, we need some kind of cumulative distribution function, the probability for a function of x and beta. And the problem is that the marginal distribution for each error term is no longer, these distributions are no longer independent. So they're all interrelated through this complex multivariate expression. And to get the marginal distribution for each observation I, we need to set it up properly by integrating out all the other random variables. And in the spatial case, the distribution has the dimension of the number of observations. So the distribution can be written as an n-dimensional multiple integral, and to pull out one of these for the marginal distribution, we have to integrate out the n-1 remaining ones, which is a major computational challenge. So putting that aside for a second, let's look formally what this means in terms of our threshold condition. And remember, everything now is a vector and a matrix, so no more individual sub-i's because we cannot really express them that way. We have to keep into account the whole joint nature of the distribution. So we proceed the same way as before. We are interested in the probability that the latent dependent variable crosses the threshold, which is the probability that the reduced form crosses the threshold is larger than 0, which we can again express exploiting the symmetry of the error distribution as I minus rho W inverse U, which is a vector condition, that's a vector of random variables, one for each observation, less than I minus rho W inverse XB, which is also a vector. So for each, we need to find the corresponding term for each of these. For simplicity's sake, we can write this as the probability of epsilon sub I as a function of rho and a function of the weights, actually, less than a complex expression in the explanatory variables, the beta parameters and the rho parameters. So this is quite complex because we really need to evaluate this in n dimensions. In n dimensions, we need to actually, for each element in the column vector that we obtain by pre-multiplying xb by this inverse matrix, we need to find the cumulative probability of the marginal error term from a multivariate normal distribution. So this is quite complex, and we'll revisit that when we talk about maximum likelihood estimation. The important concept here to keep in mind, which is very different from the classic Probit, is that the marginal conditions, the conditions that we use to set up the probability that y sub I equals 1 given the explanatory variables, that becomes a very difficult thing to set up because it's a marginal distribution from a full multivariate normal distribution. Okay, the Tobit, we won't go into any technical details. It's very complex. It's the same general setup, but the threshold condition now is the marginal of a truncated multivariate normal distribution. And just as in the classic Tobit, we have a mix of the censoring part, the unobserved part, which is the 1 minus p part, and then the regression part. Now, the complication is that the 1 minus p is not going to be a simple marginal condition, but becomes the marginal of a multivariate normal distribution. And then the observed part will be related to a truncated multivariate normal distribution. So this is all very complicated. One point to revisit is the distinction between a simultaneous and a conditional model. The simultaneous model is a straightforward extension of the linear regression case, but applied to a latent dependent variable, so an unobservable latent dependent variable. The conditional model is unfortunately how this is often interpreted, and we discussed this when we introduced the spatial lag model in the regression case, that it's very tempting to think of it as, in a conditional sense, as given the values for the neighbors, this is what we observe at a given location. And so in the latent variable context, given the variable for the neighbors could mean the observed y sub j for the neighbors. So the dependent variable remains latent, but on the right-hand side, the latent spatial lag is replaced by an actual observed spatial lag. Now, this is very tempting. It makes everything easier. It makes estimation easier, but there's a catch. And the catch is the same as in the linear regression model, namely the spatial lag model is really a model about feedback effects. Feedback between a location and its neighbors, and then the location in terms influencing the neighbors. And remember the expression that I am my neighbor's neighbor, so if I am influenced by my neighbors, then I in turn will influence my neighbors. In a conditional model, that aspect is ignored. So the conditional approach ignores the feedback between the latent variable back to the observed neighbors that is just factored out. The advantage of the conditional approach is that it can be estimated as a standard Probit model, but only for observations that are far enough apart in the sense that we can ignore the feedback effect of the latent y star on the observed y. So if observations are spread out far enough, then that feedback effect is contained to the specific observation. It doesn't spread through the system. It still is only partially captured, but at least the observations on the observed dependent variable can be treated as if they are uncorrelated, and so therefore standard probit can be applied. This is called a coding method, and the coding method consists of subsetting the observations into little islands, so to speak, an island with an observation and its immediate neighbors, such that there is no overlap. The difficulty in doing this in practice, and typically the weights matrix is used to decide whether or not two observations are neighbor, but we have already seen this, that the weights matrix is not the variance covariance, and what really matters to establish uncorrelatedness is the structure of the variance covariance matrix. And we've seen, for example, that for autoregressive processes, the range of the dependence, the range of the non-zero values for the correlation is much wider, goes much beyond what is specified in the spatial weights matrix. So for most practical purposes, it's not a good idea to take the conditional approach. It might be a way to apply standard estimation procedures, but only if you have lots and lots of observations, so that the subsampling doesn't really matter that much. But nevertheless, the feedback effect is underestimated. So that's for the spatial lag. The spatial error, Tobit and Probit, is actually much simpler because we don't have to deal with this reduced form. We just have a spatial autoregressive error, which, as we now know, has its own expression in a reduced form, which we then plug back in, and which gives us a multivariate normal distribution with this complex variance covariance matrix, I minus lambda w prime I minus lambda w, inverted, the whole thing inverted. So in terms of the probit, we don't have this complication of having to have a reduced form on the right-hand side. We just have to deal with the nature of the distribution. And again, we have the same problem. The threshold condition here for U sub I is really a marginal from a multivariate normal distribution. It's not a marginal from an independent set of normal distributions. And this multivariate, as we know, is non-diagonal. There's correlation, but also it's heteroscedastic. And so we have to deal with the heteroscedasticity, the non-constant variance, and we also have to integrate out the n-1 other dimensions. One approach, which we'll revisit when we talk about estimation, is just to focus on the heteroscedasticity. So then the threshold condition becomes something like this expression that the probability of U of I divided by sigma I must be less than xi beta divided by sigma I. Of course, as we already know, there is no way to estimate individual sigma i's. That just can't be done. So this is only for the purposes of spelling things out. The spatial error Tobit, again, is much more complicated than the Probit, but it's the same principle, only now the censoring is applied to the marginal of a multivariate normal distribution. The truncation is also based on the marginal from a multivariate normal that's truncated. We have the complexity of the induced heteroscedasticity, and we have the complexity of the spatial autocorrelation. So this is not a simple model, and it's actually no surprise that there's very little application of this in the literature. It's just very complex, and this is coupled with the fact, as I mentioned at the end of the previous section, that the Tobit model is very sensitive to misspecification. So you combine the sensitivity with the difficulty of expressing and estimating the model, and you can see that it's not that popular. So the next section will deal with actual specification tests and estimation of the spatial Probit and Tobit models.